Hey guys, welcome back to chapter 13. Today we're going to move into the final category of problems for chapter 13. So just as a reminder, we did a couple types of problems where we did not have to use ice tables. So we determined equilibrium constant given all of the values at equilibrium. We determined equilibrium concentrations of one unknown if we know Kc, so we knew all of the equilibrium concentrations, we knew Kc, and we could determine one unknown. So both of those were without an ice table. Then we introduced this new tool, the ice table, and we were able to fill out the entire ice table with numbers. So we knew initial concentrations, we knew one equilibrium concentration, and the entire ice table was filled out with numbers. Now we're going to get to the last of the problems. This one is kind of like the grand finale. It's the hardest of the four. And so we're going to spend some time, probably 3 or 4 videos, working through these. So the last one is to determine the equilibrium concentrations when we know Kc and we only know the initial. So this one is by far the most realistic. Measuring concentrations at equilibrium is actually a pretty difficult thing to do. How do we isolate the product? How do we measure the product's concentration? How do we isolate a reactant? How do we measure a reactant's concentration at equilibrium? So this is probably the most realistic, but definitely the hardest to solve. The big difference between this one and the previous one with ice tables is the fact that we cannot fill our ice table out with numbers. What we're going to see is these ice tables will involve x's, and then we'll solve for x, and we'll need to use some fancy algebra to do that. So that's what makes this one a little bit more difficult. The best way to do these is just to dive in. We're going to dive into an example in this video, and then I'm going to post some more videos with more examples. Okay, so here's our first example. Suppose we have a reaction mixture when the initial concentration of A is 1 molar, the initial concentration of B is 0. We know the equilibrium constant for this reaction is 0.33. We want to find the equilibrium concentrations. So the whole purpose of this exercise is the following. So it says find the equilibrium concentrations. So the whole purpose of this exercise is to solve for this portion of the table. Once we have the numbers for this portion of the table, that means we have finished solving the problem. Okay. The other thing I want to point out here is I just ran out of room on the slide. So I did not give you the balanced chemical equation for this problem. That will always be included. But I'm going to kind of sneak it in here. It's that same one we looked at a while back where it was A reacts to create 2B. So that's the balanced chemical equation for this one. Okay. All right, so what do we know? We know we need to write an ice table, because it talks about initial. So anytime there's the word initial, we know it's going to be an ice table. And it says the initial concentration of A is 1 molar, so we went ahead and put that in. The initial concentration of B is 0, and we put that in. That's all we know. Okay. I'm also going to sneak this coefficient in here because I like to put that there just as a reminder when I start to fill out the ice table. All right, I got no more numbers to put in. I have no way to determine what numbers I'm going to put in, okay? So here's the big difference. Here's kind of what makes this difficult. I do know a little bit about this change, right? So let's start with the product side. We've got 0 products, none at all. What is the only way that that can change? Can I take product away so it is a minus? Or do I have to add product or make product? The only way for 0 to go realistically is to go up. So I know this change is going to be a positive number. if we are creating the product, and we are, we've got to use up our reactant to do that. So I know the concentration of this is going to go down. Now, what is that change going to be? Well, I don't have a number to put in there, but I'm going to use the value x. So this is going to change by some value x, and I know that the concentration is going to go down. So it's going to change by a value of minus x. And I know that this is going to change by a value of plus x, but I also have to acknowledge that we're going to make twice as many of these. So for every one of the A's that break down, 2 of the B's get formed. So A to B. So this is going to go down by a factor of x. This is going to go up by a factor of 2x. That's the best I can do for change, okay? But now I can fill out this equilibrium. So 1 minus x will be the value at equilibrium. And down here will be 0 plus 2x, or just 2x. So here's the big difference. This table is filled with x's. It's not completely filled with actual numbers. And solving this is a little bit harder. Okay. So I'm going to jump forward here to this slide. It gives me a little bit more room to work. The ice table is filled out. That's exactly what we did on the previous slide. Now we're going to use this last piece of information that it gives us. The fact that K equals 0.33. So up here, I'm going to write that K equation. So K equals products over reactants. So the concentration of B at equilibrium squared times the concentration of A at equilibrium. I have some values that I can put into this equation now, right? I know that K equals 0.33. How do I know that? That's what the problem told me. K equals. So I know that value is 0.33. I also have equilibrium values that I can plug into this equation, okay? So on the top, I can put the concentration of B at equilibrium is 2x. And we're still squaring that. And the concentration of A at equilibrium is 1 minus x. So while this is not a pretty equation, it is an equation that I can solve algebraically. If I can isolate x and solve for x, then I know that I can figure out the equilibrium values. So let's solve for x. I'm going to jump ahead to the next slide because I'm going to need a whole lot of more room. All right, so here we are. 0.33 equals 1 minus x and 2x squared on the top. All right, so first thing I'm going to do is get this 1 minus x out of the bottom. So I'm going to multiply by 1 minus x. 1 minus x on the bottom, 1 minus x on the top. Those cancel. Whatever I do to the left side, I also have to do to the right side. So I'm going to multiply this 0.33 by 1 minus x. So over here, we've got 2x squared. And then I'm going to distribute this 0.33 through. Okay. So 0.33 times 1 is 0.33 minus, and then 0.33 times x is 0.33x. Okay. It's messy, I know, but we can do it. All right, now I'm going to clean up the right-hand side here. So I'm just going to rewrite this down. So 0.33 minus 0.33 0.33x. I'm going to square this, so 2 squared is 4. X squared is x squared. At this point, I recognize that I have a quadratic equation. Quadratic equations require me to get it into the following format. I'm going to kind of click ahead here. Okay. So here's our quadratic formula. If I can get it into this format here, I can plug these values for A, B, and C into the quadratic formula, or better, I can plug in these values for A, B, and C into a quadratic formula calculator, and it will spit out the answer for me, okay? So the first step is to get our equation into this format, A, B, C, and then we have it equal to 0. So back to our work here, okay? I've got 4x on the right-hand side. I'm now going to move these 0.33s over. This is addition and subtraction, so I have to do the inverse to move it over. So to move this x1, I'm going to take plus 0.33x. That cancels. Whatever I do to the left side, I also have to do to the right side. So I'm going to add 0.33x. Now I'm breaking this down into 2 steps. If you're proficient and can do it in one, great. So now I have 4x squared plus 0.33x. These two canceled, so we're left with 0.33 on this side. Now to move that 0.33 over to the left-hand side, again, I'm going to do the inverse. So the inverse is subtracting. So minus 0.33. Those cancel. Whatever I do to the left side, I also have to do to the right side. So we're going to subtract 0.33. Okay. Now we have the following. The only thing left over here is 0. We've got 4x squared plus 0.33x minus 0.33. Okay. We now have it in the format of that quadratic equation, right? We've got whatever is attached to x squared is our a value. Whatever is attached to x is our b value. Whatever doesn't have that variable is our c value. So here's where we're at. A is 4, B is 0.33, and C is negative 0.33. So notice how this is plus C, and we had minus that. So another way to kind of rewrite this is that's negative 0.33, and then we can put an addition sign, okay? So something to keep an eye on. That's a opportunity that students make mistakes quite often. All right, from here, if you would like to, you may plug these values into the quadratic formula. Go for it. If that's your thing, do it. I, however, will recommend using a quadratic calculator. If you're taking my hybrid class, you would have a quadratic calculator available to you in class. If you're taking my online class, I highly recommend that you program that quadratic calculator into your smart calculator. So both of those are great options for solving these. Okay, so I'm going to take this and I'm going to plug it into a quadratic formula calculator. All right, so I think I have one pulled up here. All right, so remember our A value was 4. Our B value was 0.33. and our C value was negative 0.33. Okay, so I plug in my values for A, B, and C. I hit calculate, and it's going to spit out two answers. Okay, it will always spit out two answers because that's just the nature of the quadratic. If you look at the formula, it's negative b plus or minus. So if we did negative b minus the rest of it, that's one answer. Negative b plus the rest of it, that's another answer. So it will always spit out two values. So theoretically, both of these values solve the equation. Practically, for chemistry, applying it to our problem, only one answer will make sense. Only one answer will make sense. Okay. Get my PowerPoint pulled back up here. All right, so the two values that it gave us, it solved for x for us, right? And the two values that it gave us were the following. So it gave us that x equals 0.249 and x equals 0.331. Okay. Now let's remember where those values go. So we solved for x, right? And so it told us that x equals 0.249 or x equals negative 0.33. So the value that we solve for gets plugged in here at the equilibrium. Okay. Once we plug in x, we say x minus 1. Once we plug in x, we say 2x, and that will spit out the value of our products and reactants at equilibrium. Now, which one of these does not make sense? If I plug in negative 0.33 right here in the product side, does it make sense that the concentration of our product after this reaction is done is a negative value? Does a negative concentration make sense? No, it doesn't, right? So that tells us that while theoretically this is a solution to the equation, practically it is not going to make sense for us. So the value that we're going to move forward with is that x equals 0.249. That's the only one that makes sense to us. Okay. So now what I'm going to do is I'm going to plug that value into this equilibrium column. Okay. So the there's not helpful. The concentration of A at equilibrium is 1 minus x, which is 0.249. So the concentration of A at equilibrium equals, put this in here, 1 minus 0.249. And we get a value of 0.751 molar. And then the concentration of B at equilibrium is 2x. So the concentration of B at equilibrium is 2 times the 0.249. So the concentration of B at equilibrium is 0.498. that's the answer. So to summarize, we are given the initial concentrations. We are given the equilibrium constant K. We are asked to solve for concentrations at equilibrium. To do this, we need an ice table, and our ice table will be filled out with not actual numbers, they'll be filled out with X's. If that results in a quadratic equation, then we solve for the quadratic equation. We pick the X value that makes sense, get rid of the one that's silly, and then we're able to solve for our equilibrium concentrations of our products and our reactants. I hope you guys found this helpful. There'll be more examples to come in the future.